Good evening again.
Good evening.
It barely seems like half an hour since I was last talking to you.
So many seconds is that?
At least 3,000 seconds, I think. But last time I was talking about something rather down to earth, definition of a second and the rotation of the Earth. Here we're getting about as far away from that as it's possible to be. We're talking about imaging a quasar, which is on the other side of the observable universe. So, do people remember 2020? Something happened in 2020. Life changed. And life changed mainly because of this object, which will remain nameless. But it got us looking down at the floor or the ground or the pavement and being told to keep our distance from other human beings. But when I was told to keep my distance from other people, I sort of remembered what Stephen Hawking had to say. Remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. I thought, yep, that's a philosophy to live by. So during the lockdown, I thought, what can I do? Well, I can keep my distance from other people, but it would be interesting to see just how far could I possibly look in the astronomical sense? What's the greatest distance you can probably expect to find something? We know that with the naked eye, we can see as far as, for instance, the Andromeda galaxy, 2.5 million light years away. But what is the limit to how far we can see? So I thought, let me set myself a challenge. We know that the universe is vast and the universe is ancient. And we know that large telescopes, doesn't matter which one, are able to image galaxies billions of light years away. We know that the Hubble Space Telescope and now the James Webb Space Telescope and all these huge telescopes on Earth are able to see galaxies many billions of light years away. And I thought to myself, is it possible to capture an image of one of these objects without using a telescope? In other words, I've got a camera, I take pictures of wildlife. Is it possible to use my camera and take a picture of one of these extremely remote objects? Spoiler alert, yes, otherwise I would not be giving this talk. I found a paper, we don't have to worry about the details, but I found a paper that produced a survey of lots of quasars. Now, first thing is, what is a quasar? Well, a quasar is basically the nucleus of a galaxy that's emitting a huge amount of energy, and hence it's visible from great distances, billions of light years or so. Virtually all of these quasars almost certainly are supermassive black holes. So an artist's impression of what might be going on might look a little bit like this. We think these quasars are very energetic supermassive black holes that are gobbling up and feeding on a lot of matter, perhaps gas, perhaps stars, it doesn't really matter. A lot of stuff is falling into the supermassive black hole and generating an enormous amount of energy. So enormous that these things are visible from very great distances. So this survey basically looked at all of the quasars that were known, that were particularly luminous, and I looked at where they were in the sky, and I picked one that was visible from the UK. This was in the summer of 2020, so I wanted a quasar that was somewhere in the sky, that was nice and high in the sky, as seen from the UK in the middle of summer. And I found one that was quite luminous and in the right place at the right time. And it goes by the wonderful name of J161737. Okay, it's a stupid name, but it's basically the coordinates of this particular quasar. Now, these people who'd done the survey of these various objects looked at the spectra, because ultimately the spectrum of an object tells you something about how far away it is. One thing that will come out of this talk, I hope, is the realization that we cannot actually measure the distance to remote galaxies. We can't measure how long the light has taken to reach us. The only thing we can do is look at the light that arrives from these remote objects and hopefully deduce or calculate distances and times. So the spectrum of these remote objects is very important. And it just so happens that for this particular object, they looked at the spectrum. It doesn't look very spectacular, I agree, but they identified, for reasons we're not going to go into, they identified the biggest peak here as being redshifted. In other words, the light left this object quite a long time ago, presumably, and the light has been stretched. Its wavelength has been increased because of the universe that it's crossed in the length of time it's taken for the light to arrive here. They have deduced that that particular peak should be in the ultraviolet part of the spectrum. Here's the wavelengths in angstroms. 10 angstroms is 1 nanometer. So there's the blue end of the spectrum and the red end of the spectrum. This thing appears in the red end of the spectrum, but it was emitted by the object in the ultraviolet. And they've calculated that that peak, when it left the object, had a wavelength of 1200 angstroms, and it's been redshifted by the stretching of the light traveling through a universe which is expanding, and it's been stretched from 1200 to 6500. And redshifts, in other words, the amount of stretching, rather than talk about where it should have been and where it ends up being visible, the redshift is quantified by a simple ratio of how much has it increased by compared to how much was it in the first place. In other words, redshift is simply given a number, which in this case would be the difference between 6500 and 1200 divided by 1200. That gives us a redshift of 4. So we don't have to worry too much about the details, but essentially this light has been stretched by not just a few percent, it's been stretched by a lot. So what does a redshift of 4 correspond to? Well, it corresponds to it being a long way away. We'll look at the distances shortly, but a redshift that's much bigger than a fraction of 1 must be a very remote object. So this seemed like a suitably distant object, and it was in their catalogue, and it was luminous enough, and it was in the sky in the summer of 2020. So I thought, that's a target. I want to try and photograph that and see if it's possible. So I took my camera. The camera that I use for normal daylight photography is a Nikon camera, and I have a telephoto lens that I use for wildlife photography. So I put my camera on a tracker. A tracker is basically just a motor in a box. That's really all it is. It's a motor in a box that will turn the camera at 1 revolution per day. So as the Earth rotates, this box will rotate the camera in the opposite direction, and hence the stars will be static in the field of view of the camera. It's effectively a small telescope mount, if you want to think of it that way. I think of it purely as a camera tracker. So this particular one was an ioptron. It doesn't really matter what type. And I used a 300mm lens because that's the favorite lens that I use when taking pictures of animals. And the camera itself is not modified in any way for astrophotography. It's not an astro-modified camera. I haven't played with the filters. I haven't taken the infrared filter out of the camera. It's exactly as it comes effectively out of the box. It is precisely the same camera body and lens that I have used on safari. So this camera and this lens have taken this picture of zebra, and the question is, if this setup is capable of taking pictures of zebra, is it also capable of imaging a quasar on the other side of the observable universe? It would be quite incredible if the same technology can do 2 different jobs. But I figured, what the hell? If you don't try, you don't know. So, according to the catalogue, this particular quasar that I was after is in the constellation of Draco. And for those that know their constellations, Draco is overhead during the summer months. And the rectangle shows the field of view I was expecting for this particular 300mm lens. The small dot at the center is a star of 5th magnitude, and I looked at the coordinates of the quasar and the coordinates of the star, and I figured the quasar ought to be fairly close to that star. So that was quite handy. I knew there was a bright star fairly close, so I could use that as a guide to make sure I was looking in the right direction. And then I wanted to take the longest exposure I could. I had no idea what exposure I would need. This is July, and therefore there isn't much night. Basically, in between the end of evening twilight and the start of the dawn twilight, you haven't got very long in the middle of summer. And I took, roughly speaking, an hour either side of local midnight, midnight meaning 1 o'clock BST. So I took exposures, roughly speaking, for 2 hours over the darkest part of the sky, over the darkest part of the night. I didn't take one long 2-hour exposure. For those of you who've dabbled with astrophotography, you know that's not normally how you do it. I took a large number of short exposures and then added them all together to get this result. During the 2 or 2 and a bit hours that I was imaging, some clouds came over. So I threw those frames away before stacking the remaining frames to get this equivalent of a 2-hour exposure of the sky. So there's the 5th magnitude star in the middle. I was expecting that that quasar, if it's going to be visible, should be in the middle of that square according to its coordinates. So I took the original image, some 20 megapixel image or something, and I zoomed into that region where I expected to find the quasar. And I checked the coordinates, and that is it. I double-checked by doing some plate solving and made absolutely sure that the coordinates of that dot in the middle are absolutely where that quasar is supposed to be, and there are no other stars that are anywhere close to it. So that is quite definitely the quasar that I was chasing. Most of the light from this quasar is focused into just about 1 pixel. Although the camera had 20 million pixels, only one of them actually caught this quasar. If we blow it up a little bit further, I've just exaggerated the contrast just a little bit. You can see most of the light has gone into 1 pixel and maybe a little bit of light into the neighboring pixels. So just 1 pixel of the 20 megapixel image was actually used in that sense for this particular image. Just as a little bit of an aside, what might we expect if we've got a lens of a particular aperture, the front element of this particular lens? We can work out what resolution would we expect. What's the closest pair of stars that we could possibly resolve? What's the resolution if the lens was absolutely perfect? Okay, Nikon make good lenses, but they're not perfect. So this is just a theoretical limit. If there was no aberration at all, what might we expect from a 300mm f4 lens? And the smallest thing we could hope to resolve is approximately 9 microradians, 9 millionths of a radian. You don't like radians, you prefer arc seconds. So that's a little less than 2 arc seconds is the smallest thing I could hope to resolve with this lens. The camera on the back end of this has got pixels of a particular size, and it turns out that the size of the pixels when used with this lens were approximately 15 microradians, or about 3 arc seconds apart. So the resolution of the lens is reasonably well matched to the separation of the pixels in the camera itself. And just to give you a little bit of context, if you take an object the size of the Milky Way and think about the distances we're talking about, then an object like the Milky Way would be expected to be about 2 pixels or thereabouts. So we're talking about an object that is much smaller than a galaxy. It's just the core of the galaxy, the nucleus of the galaxy. Okay, so it seemed to work in that I caught something which I've identified as the quasar. But before thinking about anything else, I just looked and thought, well, I wonder, is there anything else in the image? In other words, I checked against a catalogue of objects and identified that in this particular 8 arc minutes by 8 arc minutes crop from the original image, there's actually 10 galaxies in there, apart from the quasar itself. Some of them are quite definitely non-circular. You can see that they appear to be elliptical or at least stretched out. So these are definitely galaxies. But of course, there are some objects in there where you can't really tell if they're a star or a galaxy. So it's only by comparing with a catalogue that I've determined that those aren't stars, those are actually galaxies. So if there are 10 galaxies, I didn't do this for the whole image, I'm just not patient enough to do that, but if there are 10 galaxies in that tiny little crop from the image, then there's probably about 7,000 galaxies in the image itself. So that's just a sobering reminder that, yes, the Hubble Deep Field can take thousands of galaxies in one picture if it takes a 1 million second exposure, but you, with your camera in your back garden, can also capture a few thousand galaxies if you so wish. But that was just on a little bit of an aside. The real question is, okay, I've caught this quasar, it's got a redshift of 4, but just how far away is it? And there's the problem, defining what we mean by the distance. The galaxy, it doesn't matter if we talk about quasars or galactic nuclei or galaxies, let's just think of it as a galaxy. Light left this galaxy a long time ago, and the light obviously made its way towards the Earth. So we could define the distance as being how far away was the object when the light left the object itself. But of course, it's taken a long time for that light to arrive. So the light has been traveling from the galaxy to Earth, and during that time, the universe has continued its expansion, and so the galaxy is getting carried further away from the Earth. There's a certain recession velocity. So we could say, well, how far has the light traveled to get to us? That's another way of defining the distance. And of course, by the time the light actually arrives at Earth, at which point we can measure it and work out what its redshift is, the object has got even further away. So defining the time now as being when the light arrives, we can ask, well, how far away is the object now that the light has actually arrived at Earth? So there's lots of different ways we could define the distance. Is it the distance when the light left? Is it the distance when the light arrived? Or is it how far the light has traveled? All those three are different distances. So there's no such thing as the distance. If you ever talk about the distance to a very remote object, you ought to specify which one you're talking about. If the object's very close, then all of those distances are essentially the same thing. But if the object is very remote, these three distances can be quite different. And it's rather tricky to get this middle one here, because if you think about it, the light is traveling from a distant galaxy to us through space, but as it's traveling through space, the universe is continuing to expand. In other words, the light is traveling through space, which is itself expanding. And therefore the light, it's a bit like saying, if you're swimming through water, but if the water is flowing against you, then your speed is going to depend on not only how fast you can swim, but how fast the water is going. Or another analogy is, think about an ant moving along a rubber band. If the rubber band is static, the ant moves a particular distance along the rubber band in a particular time. But what if, as the ant is walking, you are stretching the rubber band? Then how are you going to define how far the ant has walked? It's like having a ruler on the rubber band, but the ruler continually changes because the ruler's getting stretched. So defining these things is a little bit tricky. And we have to remember that, again, we cannot actually measure the distance to the remote object, either when the light left or when the light arrived. We cannot define how long the light has been traveling. The only information we have is when the light arrives, we can measure its wavelength, and if we can deduce that its wavelength has been stretched by this much, if we understand how the universe is expanding, then we can calculate where it was when the light left. We can calculate where it is now. We can calculate how long the light has been traveling. So that's what I did. I put the numbers in a spreadsheet, and as a function of redshift, as a function of how much has the light been stretched when it arrives, we can work out where was the object when the light left, the blue curve, how far has the light traveled, the light travel distance. It's effectively the same as how long the light has been traveling, because we know what the speed of light is. So if we know how long it's been traveling, we know how far it's traveled. And also the red line, now that the light has arrived on Earth, how far away is the object now? So those are three separate distances. Note that all the distances are essentially the same if the object is quite close. If the redshift is just a tiny, tiny fraction of 1, then the distance then and the distance now are essentially the same distance. The universe hasn't had time to expand much if the object is very close to us. But if the object is very distant and the light has taken a long time to reach us, the universe has had a lot of time to expand and continue expanding while the light was on its way, which is why these three curves start to deviate compared to the very early part here. So this particular quasar, according to the team that have done this survey, they tell me that this quasar has a redshift of 4. And from our calculation, if we've calculated correctly, if we are correctly taking into account the expansion of the universe, that tells us what these three numbers are for a redshift of 4.3. And it turns out to be those three numbers there. Just to simplify things, let's just get rid of the curves themselves and just concentrate on those three numbers. So a reminder of what it actually means. According to this calculation, then the light that we saw in the image a moment ago left the galaxy 4.6 billion it was 4.6 billion light years away when the light was emitted. So the distance to the object was a little less than 5 billion light years. And it has taken 12.4 billion years for the light to arrive. And remember that the universe is only 13.8 billion years old, which means the light has actually been traveling for something like 90% of the entire age of the universe in order to arrive here. It must have left this object when the universe age was only some 10% of what it is now. So for 90% of that age of the universe, that light has been on its way to us. And now that it has arrived here, that object has continued to move away, because as the light was traveling towards us, the universe was continuing to expand, and so that quasar is now some 25 billion light years away from us. Some staggering numbers. But you can still do a very crude back-of-the-envelope calculation and say, well, it's taken 12 billion years for the light to arrive, but during that time, the galaxy has gone from a distance of 5 to 25 billion light years. So how much has its distance increased by? 5 to 25 is about 20. So during 12 billion years, its distance has increased by 20 billion light years. So what we deduce is that during those 12 billion years, the distance has increased by more than 12 billion light years. And if we do a simple calculation and take averages, the average speed, distance over time, distance has increased by 20 billion light years and a time of 12 billion years. So its speed has been, on average, 1.6 times the speed of light. Space is allowed to do that. You can't move through space. You can't get any object to move through space faster than light, but it is possible for galaxies to move away from us at faster than the speed of light. Most of the galaxies you see in the Hubble Deep Field are moving away from you at more than the speed of light. Only a few galaxies are so close to us that they actually are receding from us at less than the speed of light. So the speed, 1.6 c. And at first that sounds wrong, but when you remember that we're talking about the expansion of the universe, not an object moving through space, then that is perfectly okay according to Einstein's general relativity. In fact, not only can we say if we know the redshift, we can work out these distances, if we know the redshift, we can work out the velocity. That's only an average. That's the average speed that this quasar is moving away from us during the entire time that the light has been traveling through the universe. But we can, if we wish, calculate it as a function of time. When the light left this quasar, it was receding from us at 2.2 times the speed of light. And then it started slowing down. So this is recession velocity. How fast is this object moving away from us as a function of time? 0 is the Big Bang, and this light left at about 1 and a bit billion years after the Big Bang. And it started slowing down, but it didn't continue to slow down. After a while, it started to go faster again, and it's now back up to 1.7 times the speed of light, having dipped to a minimum of about 1.5 times the speed of light. If the universe is expanding, we might assume that gravity is pulling on everything, so surely the expansion of the universe should be slowing down, because gravity is always pulling on everything. But it was a surprise 2 decades ago to find out that the expansion of the universe is actually accelerating. That's why this curve is going up, because everything was moving away and slowing down, but a few billion years ago, everything seemed to turn around, and now things are moving apart from each other at an ever-accelerating rate. And basically, we don't understand why. We call it dark energy, but that is just meaningless. That's just a label we use for our ignorance. We don't know why the universe expansion is accelerating. If we give it a label like dark energy, it sounds really cool, but it doesn't actually help us understand what's actually going on. But that's what we're looking at with that curve. After initially slowing down a bit, the quasar is now accelerating away from us. And it's been accelerating away from us for quite a few billion years now. But it's sobering to realize that this curve has never gone below 1. It started with a recession velocity faster than the speed of light, actually faster than twice the speed of light, and it's still there, and at no point has it ever fallen below 1. And then you end up with the almost paradox of, if this object is moving away from us faster than the speed of light, how did the light get to us? And that's a slightly more tricky problem, but it is actually possible to explain how that happens. I'll move on and come back to that if there's any more questions about that. So it is possible for light to reach us even though the object is moving away from us faster than the speed of light. Let's just have a final look at a diagram which sort of makes the point. This is distance from us, 0 to lots of billions of light years, as a function of time. So Big Bang down here, and we, of course, on a time scale, this is time upwards, not perhaps the usual way of plotting it, but this is time upwards. So we are here, 0 distance from us, and of course we are 13.8 billion years after the Big Bang. The light from the quasar left when the quasar was about 4 or 5 billion light years away from us, hence that position, and it happened after the Big Bang, about 1.5 billion years after the Big Bang. So from the green to the orange, that's about 90% of the history of the universe. So there's everything from the Big Bang to us. That's about 90% of the age of the universe. That's the light from the quasar to reach us. So if the light was released at this point, and then we've captured it at that point, then can we plot where the light went in terms of, at any given time, where was the light in terms of the distance from us? And you might at first assume, well, if the light left there and it's coming towards us, then presumably the light followed that particular line there. No, because the universe is expanding. The light is trying to get to us. It's heading in our direction, but the light is moving through space, which is dragging it backwards because the space is expanding faster than the speed of light. It's like a swimmer going at a particular speed through water, and the water is flowing faster than the swimmer can swim. So what's going to happen? The swimmer goes backwards. So in fact, what happened for the first few billion years, because of the recession velocity of that quasar, the light actually went backwards. So in other words, after the light left the quasar, for a little while, the light was further away from us. Even though it's heading in our direction, but getting pulled backwards. So for a couple of billion years or so, it actually got further away from us. Eventually, the light clawed its way through space to the point where it could start to make headway. That took a few billion years, but after about 4 billion years or so, it started to make headway and eventually found its way to us. So it's really weird. It's not intuitive because our brains are not wired to think about things changing as a function of time. The distance from Liverpool to High Legh is a certain number. It doesn't make any difference if you walk it or take a car or take a Trans-Pennine Express train. Well, maybe not. But the distance between 2 points doesn't depend on how fast you travel between those 2 points. But when we're dealing with an expanding universe, you have to take into account how long it takes to get from A to B, because in the meantime, the distance from A to B will change because we live in an expanding universe. Over small distances, it doesn't matter. But when you're talking about the universe in the largest scale, it does matter, and you end up with really weird sounding paradoxes. They're not paradoxes, they're just weird because you're not used to thinking about what if I move from A to B and the distance between A and B change. In other words, what if the surface of the Earth was more like a rubber band rather than a fixed distance? What if the Earth's crust was elastic rather than apparently fixed? If that was the case, we'd be more used to this idea of objects moving through space in apparently weird ways. What happens to the quasar itself? The light gets dragged backwards and eventually makes it to us. What's the quasar itself doing? Well, the quasar is simply getting further and further and further and further away from us. So the quasar itself, as time goes by, simply gets further and further away. I've drawn it as a dotted line simply because it shouldn't really be a straight line. I've already shown that the velocity actually changes. It goes a bit slower and then it speeds up again. So that straight line really ought to be a curve. And I can't work out which way it should curve, so I've just, no, it's close enough. It's a straight line. After a few 12 billion years or so, it will end up over on the right-hand side of the graph at about 25 billion light years or so. So the object started at a relatively modest distance of 5, but ends up at 25 billion light years from us. And that is just plain weird. And it takes a little bit of sitting down over one or perhaps many cups of tea, or perhaps alcohol, before you can figure out that that's what is actually happening. But let me finish just with narrative rather than any attempt at graphs or maths. Because when I took this picture, I ended up with a dot, the least impressive picture I've ever taken, 1 pixel in an image. But then I started thinking about the narrative from the point of view of the light. The light left this quasar 1.4 billion years after the Big Bang. It had already been traveling for 8 billion years, even before the Earth existed, even before the solar system existed. And it continued on its way for another 4.5 billion years or so. Over the period of a few billion years, life evolved on Earth, and the light traveled on. Dinosaurs come and go, and the light travels on. In the last million years or so of its journey, it finally arrives at the edge of the Milky Way. It crosses 1 or 2 spiral arms and enters the solar system. And in the last few hours, it finally arrives at Earth, and it travels through the atmosphere in a fraction of a second, hurtles towards England, dodges a few clouds on the way, hopefully, and enters the lens and hits the camera sensor. So it was only 1 pixel in the image. But what a journey. So here's a graphical summary of what we're talking about. An ordinary camera with a telephoto lens, which is great for taking pictures of zebra. Stick it on a tracker that just simply turns the camera at 1 revolution per day to stop the stars trailing. Point it where you think the object ought to be, in this case the constellation of Draco, almost overhead. That's why I chose it. Take a long enough exposure. 2 hours was long enough. I might have got away with less, but I took as long an exposure as I could get away with. And there is the tiny pixel, what it was all about. Light travel of 12 billion years is 90% of the age of the universe, which is why I like to think of this as the quasar's ancient light. Thank you all for listening.